Okay, I think we can start. If someone will join, then it's not a problem. I hope everyone can hear me. I'm Nitzan from Almog Diagnostic, and we are happy to host here today Dr. Kader Thiam. He's SVP Discovery, Preclinical Models and Services at genOway, for a scientific lecture on genOway preclinical models.
Thank you, Nitin. So it's my pleasure to give this lecture on the different preclinical model we have here in the field of immunoinflammation and oncology. And during today's during today's talk, I'm going to walk you through the model that we are running here, which has a human immune system. By immune system, I mean lymphoid as well as a myeloid system. And I will also talk about other type of model, which are image checkpoint immunized model. So just before I dive into the presentation, please let's make this very informal, meaning that if you don't, if I'm going too fast, let me know. If I'm saying something which isn't clear, let me know. If you have any question, please just interrupt me. Okay, so my computer is on full screen, so I'm not able to see the chat or to see any kind of message that you may send. Just stop me if there is something unclear, and that would be
Yeah,
the
it's okay.
easiest way.
We will follow the chat and the question and answers. So if there will be a question or something important in the chat, we will
Okay,
see
perfect.
it. Perfect.
Okay, okay. So first, genOway, who are we and what do we do? So before I dive into the science, just let me know who's genOway and basically why are we providing those models. So basically, genOway, it's a company which was created about 20 years ago. And the company was first focused on model creation on demand. So basically, people were coming to us and asking us to develop a model based on the different target gene they were working on. As such, we've been generating several thousand of models over the last years. And this is just what we did last year. The majority of the model we developed last year were indeed a humanized model. By humanized model, I mean model in which a given mouse gene was placed by the human or ortholog, and model of target validation. Who do we work for? We just here listed the top 20 pharma companies based on the investment in R&D, and we are providing indeed model to 17 of those, as you can see here. We also work with mid-size pharma and biotech, and this slide just summarizes some of the company we work for. But we are also providing model with CRO in the field of immuno-oncology and inflammation. And as such, our model are routinely used by CROs such as Champion Oncology, Covens, Charles River, OncoDesign, Evotec, and others, and CronBio. So in Israel, which is our track record in Israel, and what have we done with Israel? So basically, we started to work with Israel, I would say probably about 13 to 15 years ago. We first started to work with some renowned academic centers, which are mentioned on this slide here, such as the Technion, but also the Rambam Hospital, the Ziv Medical Center, and we could have added also the Weizmann Institute here. And we then started to work with few biotech, which are mentioned here, biotech and pharma. And I have to be totally transparent with Teva. The work that we did with Teva was not truly with Teva Israel, but was with Teva worldwide. And some of the model went to Israel lately for their use over there. So this is in fact how we were working for the last, I would say, 16 years. 4 years ago, we decided indeed to start our own catalog of preclinical model for the assessment of agent targeting the immune system. Why did we do this? In the part of our model creation services, we did several immune checkpoint humanized model, and as such, we gained a huge experience in this. So we had the chance to work with BMS Medarex, which in fact was the inventor of one of the PD-1 modulator, which is on the market today. And we generated for them several immune checkpoint humanized model. And since we are several immunologists in the company, we started to get familiarized with this topic. And based on the increasing number of demand of people asking us to redo the same model every time, we then took the decision to generate a catalog in order to have these models available as off-the-shelf models for any pharma or biotech that would love to access this type of models. So we designed a platform which comprised two types of models. Models which are severely immunocompromised, which could be reconstituted with human cells, and this is what I will mainly detail today. But also, we decided to have a different type of model because all of those models have a great potential because they will help you to see how your campaign would modulate the immune response in a human context. They still have certain drawbacks due to the fact that the stroma around the immune system is of mouse origin, and the crosstalk between the stroma and the immune system will not be fully functional. So as such, recruitment of cell in the TME and so on may not really reflect what would happen in Mother Nature. So we decided to develop a second catalog in which, in fact, we use immunocompetent mouse model, and those immunocompetent mouse have been humanized by knock-in for certain target, and I'll show you some example on this during the talk today. This is the catalog of immune checkpoint humanized model that you're going to have access through Almog Diagnostic. You're going to have access to all the model which are here in this blue square. You will have access to this model by the end of the year. In early next year, you have access to this collection of mice as well. So all these models are fully available now. They have been validated by genOway, by different CROs such as Charles River, such as Covent, such as CronBio, but I could have included here Champions Oncology as well, but also by pharma company. I will show some examples of this in today's talk. What I wanted to let you know is that we also have access to another type of model that will be available through the collaboration with our colleague from Almog Diagnostics, is indeed a model in which the CD3 complex has been humanized. So we decided three years ago to launch an ambitious project for T-cell engager assessment. As such, we contacted several pharma companies we had connection with, and we came up with the idea to humanize the whole CD3 complex. The strategies that we followed were the following. As you know, the CD3 complex here interacts with the TCR. So you have here the TCR alpha beta subunit. And the CD3 complex has, in fact, different subunits, CD3 epsilon, CD3 gamma delta, which are here. So in order to have a functional interaction here, we must have a proper pairing between the CD3 subunits on the extracellular domain, but we must as well have a proper interaction throughout the transmembrane domain via the cell bridges, which are shown here. So our strategy in order to keep this interaction functional was indeed to humanize only the extracellular domain of the CD3 complex and keep the TM and extracellular domain murine. This model has been generated for every subunit of the CD3 complex. The models are currently under validation, and when validated, they're going to become available to you. What you have as an available model now for T-cell engager is something slightly different. Is a model in which we decided to go for, let's say, a safer approach, which in fact enables to assess approximately 70 or 80% of the current T-cell engager. So most of the T-cell engager which are available on the market today target indeed the N-terminal part of CD3 epsilon. So what we did is that we humanize this by knock-in, and we pay attention not to modify any of the amino acid involved in the binding to epsilon to delta or epsilon to gamma. And as such, this resulted in a functional CD3 complex, and those mice are available. And just as an example here, they have been validated by one of our pharma partner, where they tested different bispecific which targets the human CD3 complex. And as you can see, those bispecific do display a dose response in tumor growth inhibition here in the model of MC38 tumor growth in the mice, whereas the bispecific has no effect at all in wild-type mice, as you can see here. I'm not going to detail this model today, just to let you know that you can also have access to this model through the collaboration with Almog and Diagnostic. And if there is any interest, I'll be more than happy to walk you through this model and show you the validation data that we have with this. And needless to say that this model would then be crossed with all the immune checkpoint humanized model we have in-house. So one last point in the introduction before we dive into the science. Uh, what's the IP status for all the models that we generate and that we provide you with? To make the long story short, it's very simple. We will use either our own technologies or technologies that were by others. And in that case, genOway will take a license. And our licensing strategy is very, very, very simple. Our licensing strategy is as follows. We take licenses, which give us the right to use the technology, but we also negotiate the right to give you freedom to operate with the model that we generate, meaning that you can use this model for drug screening and R&D purposes. And if you're a CRO, you can also use this model for commercial services. That sounds obvious, but believe me, it's not the case, because in this field, many people are in fact using those technologies without having any right to do so. And just as a matter of fact, genOway today owns exclusive right for key technologies, which are the knock-in technologies and the CRISPR-Cas9 technology from Merck Sigma Millipore. And as such, we are today the only company that has a right to make mouse and rats model using these technologies, and that has a right to give you freedom to operate when you're using those models. And you know that there are many companies which are making models, so that tells you how sensitive they are about the IP right and the fact to provide you with the proper FTO. Okay, so let's start by the first model that you can have access to through genOway's and Almog Diagnostic collaboration. So as you know, today, use of immunocompromised mouse model is quite tempting for different type of uses. You may decide to use this model for reconstitution with human, for engraftment of human tumor cells such as PDX or CDX. Or you can use those mice for reconstitution with human cells such as PBMCs or CD34. First, let me talk about this. The use of immunocompromised model for engraftment of human tumor cells has been reported for now several decades, and there have been several types of model that were used in this field. To make a long story short, I'm not going to go through all the model. There are some model which display no T cell, no B cell, but they still have some NK cells, and as such, those models have a very poor permissivity to engraftment with human tissues. Then comes a second generation of model in which the T cell and B cell compartment was altered through different mutation, which could be SCID mutation or RAG mutation, and I'm going to detail this later. And those mice has no NK cell on top. And these are, in fact, the most permissive model you could use. I would focus only on model having no T cell, no B cell, no NK cells. So the model that we're using is called BRGSF. BRGSF stands for biopsy, RAG2 knockout, IL-2 receptor gamma chain knockout, sub-alpha of node origin, and FIG2 knockout. What are the outcome of those modifications? The biopsy background provides a functional complement cascade, and I'm going to comment on this later, not now. The RAG2 knockout abolishes the VDG recombination in both T and B cells, so there is no T cell, no B cell. The IL-2 receptor gamma knockout block the development of NK cells. The sub-alpha of node origin provide a proper interaction signal between sub-alpha and human CD47, and as such, you have a don't eat me signal, which is triggered, which inhibits the phagocytosis of the human cell by murine macrophages. And the FIG2 knockout reduces the mouse myeloid compartment for two purposes: better engraftment of human cells, and second, more space for the human myeloid cells to develop, and I'm going to detail this later. So how this model differs to the other model that you have access to. Here, we just mentioned the three main type of model. The model which have no T cell, no B cell because of RAG2, and the model which has no T cell, no B cell because of SCID mutation. And to make a long story short, the SCID mutation do show some weakness in the IgG appearance in those animals. And the SCID cell mutation also result in spontaneous tumor because the SCID gene is involved into DNA repair mechanism. So when you knock it out, there are spontaneous tumors which develop in those mice. None of those is reported for the RAG mutation, and both models have no NK cells. The the BRG model are indeed more resistant to radiation, and you can test any kind of drugs that you wish, which is not the case here with the NSG. And finally, as said in the introduction, the complement cascade is functional, and you have a defective mouse malware compartment, which renders the model more permissive to engraftment with human cells. So this is just a paper published by a Japanese group last year. In this paper, they wanted to compare the BRG background. The BRG background is a parental background which has been modified to add sub-alpha and FIT2. They compare this background to the NOD scale. And they engrafted here cholangiocarcinoma PDX in those mice. And as you can see, the take rate is 75% versus 6%. So suggesting that here they have a much greater take rate when compared to this, which makes sense because here there is indeed no NK cell, whereas here there's still NK cell. Once they engrafted tumor in those mice and when they selected animal in which the tumor developed, then they had approximately the same success rate of PDX growth in those mice. So the take rate would be different, but then the tumor growth would be the same. So in summary, these animals here, in contrary to the other existing background, have no leaky expression of B and T cells, no spontaneous tumor formation, and no reduced lifespan of the model. They have a complement cascade which is functional, and as such, they can be used for any xenograft study and any study involving complement-mediated mechanisms. The model could be engrafted with human cells, and as you can see on this slide, here we are showing you BRGS mice, which were engrafted with either human multiple myeloma cells, leukemia B cells, or pulmonary carcinoma. And in all cases, the tumor and the cell proliferation was observed in those mice without any major problem. Other cell lines have been tested here, but I'm not going to detail all of this in this seminar, just to let you know that you can just use this model for standard PDX and CDX studies. How this model behaves when compared to the model you're using today, which could be the NSG or which could be the NOG background. This was a study performed in collaboration with StrongBio. And in that study, they wanted to assess the ability of the BRGSF mice to be used for engraftment with AML that they had from Chinese patients. So they compared, in fact, two AML models in BRGSF versus NOD-SCID versus NOG. And the data that they shared with us over the weekend was quite nice. This is what they observed. For one of the AML cell line that they had, they clearly show here that this cell line doesn't develop at all in the NOD-SCID, whereas the cell line does develop in the NOG mice, which is here, but it has a much greater development in the BRGSF due to the higher robustness of the model. When they compare the second cell line was developing as well in the BRGSF as in the NOG mice, so no major difference. And that cell line was also developing a little bit into the NOD scale. So just to let you know that you can use indeed the BRGSF mice just for standard reimplantation procedures with tumor cells. It should work even better or as good as the mice that you're using today. And for that type of purposes, the price per animal is even slightly lower than what you're paying today for NSG. And well, not slightly, it's significantly lower than what you're paying for NSG and NOG mice. Now, what's the other part? The other part is to use indeed those mice for reconstitution with human cells. So when it comes to reconstitution, you have indeed different way to do it. You may reconstitute your animal with PBMCs. To be honest with you, that's not really what we do at genOway. We don't reconstitute with PBMCs because when you reconstitute with PBMCs, you have a immune response which is mainly T cell biased. And you will start to have a GVHD very soon after the reconstitution. So those models never last more than 3 to 4 weeks in general. Why people are using PBMCs reconstitution? Because in general, there is a wait list to get access to CD34 positive cells reconstituted in the industry. In our case, those mice are available as off-the-shelf models, so you can get them right away. As such, we focus on the CD34 positive reconstitution, which provide indeed a multi-lineage reconstitution, but I'm going to detail this. First, let me share with you what do we have as a data for PBMC's reconstitution on the BRGSF mice. So this is a study where they compared the BRG here to the NSG for reconstitution with PBMCs. And as you can see, human CD45 cells expansion in the NSG is faster in faster in NSG mice than BRG. But then the reconstitution takes longer in the BRG when compared to the NSG because there is less GVDH in those mice here. When they look at the T cell expansion, they observe a bias toward T cell in the models as it is for the NSG, and they observe more variability in the BRG compared to the NSG. When they look at the viability of the model, the consequence of this is in fact seen here, and you're getting a much higher lethality in the NSG when compared to the BRG, and that comes with signs which are indeed the consequence of a GVDH, as you can see here with the percentage of body weight change that you're seeing in the mice. So they could be reconstituted with PBMCs. They will in fact live longer than the NSG, but anyway, that's really not what we recommend to do. What we recommend to do is to humanize those mice with CD34 positive cells. How this works and why do we do this? So the principle is the following one. You take animals which are newborn, which you reconstitute by intrahepatic injection of human CD34 positive cells from cord blood origin. If that works, 12 weeks later, your mice here will develop a human immune system. This system has been reported now since almost 15 years, and you can use it with different models, ours, but also the one available from the competition. What really makes a difference here is the quality of the recipient mice that you're going to use for reconstitution. As explained previously, the model that we're using is severely immunocompromised, is permissive to reconstitution with murine, with human cells, so it has a functional don't eat me signal. It has a deficient mouse maggot compartment, and it has a functional complement cascade due to the biology background. So, and all of this will in fact will be highly reflected in the immune system that you're going to see in those mice. First, I will walk you through the permissivity of the model due to the sub-alpha which is added. So when you reconstitute those mice here with human CD34 positive cells, this is indeed what you're seeing. Here, I'm just showing you the panel of markers that were studied to identify the different cell population. I'm not going to go through the whole panel, but if you want to know tomorrow how did we identify myeloid or CDCs, we have the panel which we use here. So first, we said that we have a sub-alpha which is able to interact and to trigger a don't eat me signal upon interaction with human CD47. How does this reflect in the humanization? In fact, the results are quite striking. This is the BRG, so the mice that does not have the sub-alpha, which recognizes human CD47, versus the one that has a sub-alpha, which recognizes human CD47. And as you can see, the percentage of human CD45 cells in bone marrow, thymus, and spleen is much higher when you have a sub-alpha. So the model becomes more permissive. And this is also observed in bone marrow, thymus, spleen, and blood here when we look at the number of human CD45 positive cells. The highest humanization level are observed in thymus and spleen. And on average, we have 60% of human CD45 positive cells in leukocytes in blood of the mice which were reconstituted. This has also an impact on other cell types, such as NK cells, T cells, and it enhances the T to B cell ratio, which is always inverted in a reconstituted model when compared to human situation. We have much more B cell than T cells, and the excess in B cell, it's significantly superior to what is reported in human on a general standpoint when people work with HIS mice. How long does, so first, among the T cells, what you need to see here is that the CD4 T cell will dominate in all tissues, in bone marrow, in spleen, in blood. Okay, so you will mainly have CD4 T cells, but you also have CD8 cells and Treg, and I'll show you this at the end. The sub-alpha enhances the permissivity. We said that we also knock out a gene called FRIC2. So why did we do this? FRIC2 is involved into the development of the myeloid compartment. So by knocking out FRIC2, you have less mouse myeloid cells. And that frees up a niche for the human myeloid cells to develop upon treatment with FLT3 ligand. This is just to show you that when you knock out, indeed, FRIC2, you do see a decrease in the myeloid compartment of mouse origin. When you treat the mice with FLT3 ligand, if FRIC2 is not knocked out, the mouse myeloid cells develop. And when your FRIC2 is knocked out, the mouse myeloid cells do not respond. So you can have a reduced mouse myeloid compartment and then treat those mice with FLT3 ligand, and that treatment with FLT3 ligand will specifically activate the human myeloid cells and help them to develop. So the consequences of that FLT2 mutation are at two levels. First, that free up a niche for the human myeloid cells to develop. Second, that gives you the ability to boost the human myeloid cells development upon administration of FLT3 ligand. And this indeed is what you're seeing here. Just by knocking out FLT2, it increases the number of human DCs in the mice upon reconstitution. It also changes the number of T cells in those mice and provide a much better T to B cell ratio. Now, this, what I'm showing you here, is seen over time. These are mice which have been studied up to 51 weeks, so up to a year post reconstitution, and you still detect human CD3, human CD4, human CD8 cells in those mice, as you can see, and that was published in this paper. Now, what happened when you give FLT3 ligand to those mice? When you give FLT3 ligand, you will enhance the human myeloid cells development and accumulation in the mice. This is just a study that we did in-house where we reconstituted animals and treat them over a week with FLT3 ligand by IP injection at 10 milligrams per kg. And as you can see here, mice were bled 1 day after treatment, and we analyzed the human myeloid compartment and the human CD45 cells. And as you can see, the treatment with FLT3 ligand enhances the human myeloid cells development and enhances also the human CD45 cells development due to the cytokine which can be produced out of those myeloid cells. When you look at the myeloid cells population now, this is what you're seeing. Prior to FLT3 treatment, you have approximately 5% of myeloid cells, of DCs. And upon treatment, you have approximately 20% of DCs in those mice. So those mice do have dendritic cells that are going to develop when you treat them with FLT3 ligand. This is observable here in different tissues, in spleen and bone marrow. And here looking at other myeloid cell population, namely monocytes, PDCs, and CDCs. And from all those cell types, the treatment with FIT3 ligand resulted in an increase of the frequency of the total number and the increase of the percentage of those cells in those tissues. Same analysis on other subset of myeloid cells, eosinophils, monocytes, neutrophils, and as you can see here, you have a great increase of those in those mice as well. What happened on the NK compartment now? Same observation. When you give FIT3 ligand, you indeed result in an overall increase of the NK number. And that increase in NK number is seen in different tissues, liver, spleen, lung, in FIT3 treated mice versus FIT3 non-treated mice here in red. This increase in NK cells, it's indeed observable on the NK cell in a general manner without favoring a specific subset of NK cell, as you can see based on the different markers that were analyzed here. So we do see, in fact, an overall increase of NK. Are those NK cells functional? You know that they are, in fact, model where people need to add IL-15 transgenically to get functional NKs. We don't need to do this here. We took NK cells from those mice and we just stimulated them ex vivo to see if they do react, if they are functional. And indeed, we did then an intracellular staining for interferon gamma, and as you can see, they do produce interferon gamma. Now, the HIS mice could also be used to modulate certain type of markers which are really human-specific, which do not exist in the mouse. So as you know, today in immuno-oncology and in inflammation, people are getting increasing interest for a family of inhibitory receptors, which indeed provides inhibitory signal upon activation. This is indeed the case for ILT2 and ILT4, which are really human-specific and have no mouse autolog. So these receptors are indeed receptors with signals through ITIM domains, and they have as a ligand both conventional and non-classical HLA molecule, and the engagement of those receptors by HLA would result in a decrease of interferon gamma and TNF alpha production and an inhibition of cytotoxicity. These receptors are human-specific and they have no mouse ortholog, so you can't modulate them into mouse. They don't exist. There's other type of receptors such as the LAIR or CD305, which do exist in mouse as well, and they are known to provide inhibitory signal by downregulating IL-2 interferon gamma production while inducing secretion of TGF-beta. So they favor Treg development. So are those receptors present on immune cells developed in HIS mice? We look for them, and indeed, you do detect ILT2 expression on B lymphocyte and myeloid cells developed in those mice. That is seen in the blood, spleen, and bone marrow. Same observation was also done for ILT4, which is expressed on monocyte and DCs and not on the other immune cell type, as it is in Mother Nature in human. And when we check for LAIR1, we find it expressed on different immune cell population with a differential expression on specific effector cells such as memory T cell and so on, but I'm not going to detail those data here today, and I'll be more than happy to share this with you if necessary. So in conclusion, the immune cell developed in those mice do express certain inhibitory receptors which are very human specific. The model could be used as such to test biologics that modulate those receptors, and that's the only way to do it as a preclinical model because mouse don't express those receptors. So to recap, this is how it works. The BRGS model, which is the one that doesn't have FIG2, has mainly mouse myeloid cells. When you knock out FIG2, you reduce the mouse myeloid compartment, and that frees up a niche for the human myeloid cells to develop. When you provide FIT3 ligand, you activate the human myeloid compartment, which indeed leads to proliferation and development of DCs, monocytes, NK cells. So the way we see it is as follows, and that was in fact detailed in this paper. the presence of human dendritic cell will indeed result in a much greater antigen presentation to immune cells. And that will result in a better activation of the immune compartment in a better immune response in those mice when compared to the other model, which has only almost no dendritic cells and no myeloid compartment. Just for you to know, I've showed you data with reconstitution on newborn mice. We could provide you with mice which are already reconstituted, but you may decide to do the reconstitution by yourself. In that case, working with newborn may not be so practical for you. So in this case, you may decide to do your reconstitution on young adults, and that works as well. This is what was done here with Roche, where they use our model and they waited until the animal get 40 weeks old, and they injected those with busulfan instead of going by irradiation. And they checked for human cell into the mice 12 weeks post-reconstitution. And these are indeed a number of different immune cells they are seeing in those mice. They decided to further investigate the model and check into the spleen if they do see dendritic cells. And as you can see, they do detect CDC1, CDC2, and PDCs upon treatment with Fitz-3 ligand using the protocol we provided. Same study was also seen here in bone marrow, and they were also able to detect those here in these mice which were reconstituted at starting from young adults. So if you want to do the reconstitution by yourself, you have the right to do so, and then in that case, you could indeed do the reconstitution on young adult mice. I've showed you that those mice have a good percentage of human immune cells. Now, are they functional? Because bottom line, this is what you're interested in. This is indeed what I can show you. The first study was a vaccination study, which was performed in those mice. The mice were vaccinated with KLH plus or minus alum. In this protocol, GM-CSF and IL-4 were added at the priming of the animal, and that was added in order to maturate the human disease, and they haven't compared it with condition without GM-CSF and IL-4. This is what was observed after 2 booster vaccination. They checked for the immunoglobulin response, and they checked for the antigen-specific response by looking at IgM and IgG anti-human KLH. And as you can see, they do detect antibody production in those mice, and they do develop a humoral response upon immunization with KLH here, and we have no difference when the adjuvant is added. They then investigated the T-cell response in the animal, and again here, as you can see, when they took T-cell from those mice and ran a ELI spot in vivo, they observed that upon restimulation with KLH, they did have, in fact, a very nice cytotoxic activity in those mice. And that was specific to KLH because when they provide an anti-HLA-A2, it blocks this response. Here. Are those immune cells able to produce cytokine? Answer is yes. That's a study we conducted in-house where we reconstituted the mice, treated them with Fitz-3 ligand, and injected LPS. Mice were then sacrificed post-injection, and we checked at the different immune cells, and as you can see, once again, we are seeing an increase into monocyte, neutrophils, and other cell types. And when we check for cytokine produced, we here monitor by multiplex human TNF-alpha, human CCL2, human IL-8, and human IL-10, and we did detect cytokine produced in those mice. Could this model be used in immuno-oncology? I'm going to show you different type of study now. First study was a study performed with CAR T-cell. that was published by Pfizer and Selectis in 2028. In 2018, sorry, 2028. In 2018. So, in this study, they designed a CAR T cell which specifically targets multiple myeloma. And they wanted to see if that CAR T cell is efficient, question number A. And question B is, could they get rid of this CAR T cell whenever they finish the treatment? And in order to do so, they added a CD20 epitope to the CAR T, and they performed the depletion using rituximab. And if that depletion works, then they should get rid of the CAR T cell. But that would work only if the complement cascade worked, because this mechanism is CDC dependent. So this is the result they reported in this paper. First, when they inject the human multiple myeloma cells into the BRGS mice, they develop well. The mice which are lacking here are mice which has to be taken down just because they were, just for ethical reasons, because the tumor were growing too fast in the mice. So the human cells develop well in those mice. Second, is a CAR T functional? They injected the mice here with a tumor cell, and they treated the mice with a CAR T 2 weeks later. And as you can see, the CAR T treatment resulted in a control of the tumor proliferation in the animal. So the CAR T is efficient against human multiple myeloma. What about the depletability? When they injected the CAR T and then treated the mice with rituximab, they observed that the tumor's growth was reinitiated. So basically, the rituximab treatment deleted the CAR T, and in contrary to what you have when the CAR T is provided, here you do see the tumor growth in these animals. That CAR T depletion works because the complement cascade in these mice is indeed functional, whereas in the NOG model, in the NSG mice, those mice are on an NOD background, and in any NOD mice, C5a gene is knocked out, so you have no complement cascade which is functional. So in summary, the model could be used for engraftment with xenografts. They are highly permissive due to a function.ame signal. And CAR T could be assessed, and CAR T depletability could be assessed because the complement cascade is indeed functional in this model. Model was also used to assess biologics, and this is what was done. They were reconstituted with human myeloid cells. No, sorry, with human, they were constituted with, they were injected, sorry, with DODI cells, which are human B-cell leukemia, and reconstituted or not with human CD34 positive cells. And as you can see here, when you look at the tumor growth, the development of a human immune system in the mice does control the tumor growth when compared to mice which has no reconstitution. And this is also observable here by luminescence, when you clearly see that mice that do have a human immune system control the tumor growth prior to any treatment with drugs, which means that when you run a study with those mice, please include more animals in your study, because your take rates would be lower since the immune system is efficient. These mice were then treated with a bispecific, and they had here 3 antibodies: a bispecific which recognized a T cell and a B cell antigen, and the monovalent version of each arm of this bispecific. And as you can see, the monovalent version do not work better than the immune system alone in black here, whereas the bispecific does work. Last study, it's a study that we performed in collaboration with CronBio, with Eurosphere, sorry. They used a PDX bladder model, which expresses PD-L1. They injected those cells into the BRGSF-A2 versus, which has been reconstituted versus non-reconstituted, and they compare this to AD and MRI nudes. Here, in this case, the take rate is identical in between the different models. When they look into infiltration of human cells in the TME, they find out that, in fact, in the HIS mice, they do have an infiltration of human T cell, CD4, CD8 cells, but also B cells, and they also detect monocytes and NK cells. When they treated those animals with pembro, they observed no effect on the tumor growth. And when they assess the percentage of PD-1 positive cells in those mice, they find out indeed that they first have an increase of CD8 positive cells in the TME of the pembro-treated mice, so showing that the pembro did the job. And when they look for the PD-1 positive cells, they did not detect those because those cells are already here. Basically, the pembro goes on target and you can't anymore detect the PD-1 positive cells in those mice. So this, in fact, argue in favor of using a combo therapy for this type of tumor because PD-1 alone is not able to control the tumor growth. So it should be, but it goes on target and it does indeed increase the CD8 numbers in the TME. So you should combine it to something else. So in conclusion, on the BRGSF mice, these mice could be used for immunological study. They do have a functional immune system. They are permissive to reconstitution with human cells, and they can be used indeed with different type of drugs, antibody, CAR-T, and others. Now, how this model differs to the model you may have access to. I just made here a table which summarizes the different type of immunocompromised model which could have a human immune system. Which could have a myeloid compartment, NOGEC cell, SGM3, in our model. First, this model have spontaneous tumor which develop due to the SCID background. We don't have any here. Second, they do have a mouse myeloid compartment. We don't. Those models overexpress human cytokines at very low level, at very high level, sorry, and that overexpression is driven by ubiquitous promoter, meaning that you will have no feedback on those cytokines which are overexpressed by the cytokine produced endogenously. And as such, you're going to see some side effects that I'm going to show in the coming slides. They have a reduced B cell number and they have a reduced and immature B cell number here. The engraftment of human tissues is indeed limited to 3 to 4 months here due to the cytokine which are overexpressed. Here it is reported to be limited and people tend to say 6 months. In our case, we can keep those mice up to a year, and I showed you data with a human T cell in those mice a year after engraftment. These mice do develop anemia, and that anemia development is linked to this overexpression here that you're seeing, whereas here we have no anemia development. Finally, we have indeed, we have no side effect in those mice when compared to here. So to recap, the model could be used for immune study. It has a functional immune system. It has a functional cascade. It doesn't display GVHD when reconstituted with C34 positive cells. It doesn't has the main side effect of the other model, which display a myeloid compartment. How to access those mice? Those mice are reconstituted at genOway, and we can provide example already reconstituted. So we know that they can travel. We already send those mice to California several times without any problem. So we did some QC of humanization before sending the mice. So the QC was performed at genOway and then rechecked when the customer receives them in California, and that has no impact on the human immune system. For any model you will get from us, this is a type of QC that's going to be run. You will look at the number of human CD45 positive cells and check for different human immune cells in those mice, and the panel that we're using is shown here. We also know, but that's not our standard panel, but we also know that those mice do have TCR alpha, beta, and TCR gamma delta T cell. And this is indeed the ratio we have between CD8, CD4, and Tregs in both bone marrow and spleen when we analyze them. The standard QC that we're going to provide you with the mice is this one. Okay, so this type of model works well. However, they have a major limitation, is that they do not capture the proper interaction between immune system and stroma, because the crosstalk between these two compartments may not fully be functional. As such, we decided to develop, as I said, a catalog of immune checkpoint humanized models, which are models in which the whole immune system is mouse, but a given target has been humanized. And this indeed could be an alternative to the use of BRGSF mice if you need to have the right interaction between your stroma and your immune system. I'm just gonna here walk you through a model which is a CTLA-4 humanized model, so that you can really see how those models were developed and how they have been validated. So what should you expect if you decide to ask Almog Diagnostic to provide you with these mice? So as you know, CTLA-4 play a key role in the regulation of early stage of T-cell expansion, and it has in fact opposites, it opposes the action of CD28 mediated co-stimulation. It has two receptors, CD80 and CD86. When you block interaction between CTLA-4 and its ligand, that in fact can enhance immune response, including anti-tumor autoimmunity, and anti-tumor immunity. And we know that the expression level of CTLA-4 is key, because when you overexpress it or when you downregulate it, you have some side effects which are observed. So meaning that it is key to keep CTLA-4 expression physiological in vivo. We generated a model, and I wanted to show you how this was done. So basically, first thing we did was to look at which are the different isoforms of CTLA-4 that exist in human. In human, you have indeed several CTLA-4 isoforms, the full length, the canonical form, which is here, but you also have this isoform, which is a secreted isoform, and which could contain regulatory function because it's contained the whole extracellular domain. So having a model which has a two isoform is key, because that secreted isoform could act as a decoy and could capture the interaction with CD80 and CD86. So when we decided to generate this model, we compare the human CTLA-4 and mouse CTLA-4 sequences, and we find out indeed that the extracellular domain was different, 82% of difference over the extracellular domain. The exon 6 here is 100% conserved between mouse and human. So what we decided to do was to humanize the rest of the extracellular domain, keeping in mind that this is similar between mouse and human. The resulting of this is that we humanize CTLA-4 on the extracellular domain, and that is what we did. How our design differ to what has been reported in other papers. We humanized the extracellular domain of CTLA-4, and we did not alter any regulatory elements which are known. In the model which has been generated, they just removed the whole thing, and they removed at the same time the transcription factor binding sites, which are here, which could potentially regulate CTLA-4. I'm saying that our design keeps CTLA-4 physiological expression. Do we have any evidence of that? Yes, we do. This is indeed what we are showing here. We checked for human CTLA-4 expression in the humanized mice in red versus wild type CTLA-4 expression onto wild-type mice. And as you can see, we have the same expression level of CTLA-4 on T cells, B cell, NK, DC, and monocytes. And when we go into T cell subsets, same observation is true, which suggests that the regulation has been kept. And second, suggests that CTLA-4 is functional, because when CTLA-4 is impaired, that results in lethality of the animal, whereas here we did not see any lethality. The functionality of CTLA-4 were also tested by activating splenocyte from those mice with anti-CD3. And as you can see, we are able to show that in the humanized model, we indeed detect CTLA-4 expression on Treg, CD4 cells, and CD8 cells. Whereas, and that's expression follows the same kinetics that what you observe in wild-type mice here in blue. We finally checked the ability of cells coming from those mice to get activated with ipilimumab. And indeed, we show that ipilimumab does inhibit Treg function in a specific manner. It doesn't cross-react with the mouse CTLA-4. And that inhibition of Treg function comes with a decrease in IL-2 production and increase of interferon gamma production. Those mice were then used in order to run tumor growth inhibition studies. That study was run by Charles Iver. They provided ipilimumab over 2 weeks. And as you can see, the ipilimumab treated mice show a total inhibition of tumor growth in the CTLA-4 humanized mice, whereas it has no similar effect on the wild-type mice. They then investigated the mechanism by which ipilimumab works in those animals. And what they did here is that they studied the percentage of Treg, CD8 cells, and CD8 Treg ratio in the TME of those mice. And as you can see, the treatment with ipilimumab increases, in fact, the percentage of CD8 positive cells in the treated mice and diminishes the number of Tregs. And that, in fact, is in line with what has been suggested for ipilimumab surrogates in the literature. They then checked for the systemic effect of ipilimumab in those mice. And as you can see here, when you look at the T cell frequency and interferon gamma production in blood, you clearly see that you have an overall increase of interferon gamma production in blood upon treatment with ipilimumab, which in fact suggests some of the toxicity which is often observed when patients are treated with that antibody. Finally, long-term immune response was also investigated here. And as you can see, when mice are treated with ipilimumab and then re-challenged with MT38 cells, they don't develop tumor here. So this type of model could be used in order to assess antibody. The design of your study is really key in the outcome of the anti-tumor experiment that you're going to get. Just for you as an example here, the same study run with ipilimumab, but they decide to go for another treatment over. They come with a different treatment here compared to the Charles Iver treatment. And as you can see, they do observed an effect of ipilimumab, but it was not as drastic as what Charles Iver observed. So I really suggest here that you really work carefully on the design of the experiment, as it could really influence the outcome. So to summarize, that model expresses human CTLA-4 in a physiological manner. Its expression could be regulated as it is in Mother Nature. Ipilimumab is able to provide an anti-proliferative effect response of Tregs in those mice, and it restores IL-2 interferon gamma production. The take rate is similar to what you have in wild-type mice, so no deregulation when compared to the immune system of wild-type mice. model could be used to assess biologics targeting CTLA-4. The mechanism of action that we identified is similar to what has been reported in the literature for ipilimumab, and long-term immunological response could be triggered in those mice. Again, how the model differ to competition. First, models are provided with freedom to operate based on the licenses that we own here at genOway, and that can be transferred to you. And the regulation is much more physiological than the existing model, since in our model here, we have both expression of the membrane-bound CTLA-4 and the secreted form. And we do have the extracellular domain, which is fully humanized in opposition to what others are doing. And finally, when you look at the regulatory elements, which sustain the proper regulation of CTLA-4, we only change this exon in our model, whereas in the other model, they also knock out those regulatory elements, which could have an impact on the regulation. So I'm not going to go further here. I'm going to stop here due to time constraint. What I just wanted to say at the conclusion is that we all know that the future of oncology is in combo therapy. So all these models has been intercrossed for bispecific assessment. And for example, we just generated a PD-1 model, which also has been tested with Pembro. It works. I can detail this in another seminar. That PD-1 model was then further crossed with a CTLA-4 model. So you have the double humanized model available throughout ALMOG. The PD-1 humanized model will also cross with TIM3. Here is a set of data where you see that when you provide PD-1 alone, you have a nice tumor growth inhibition in a model NT38, but the combination with PD-1 TIM3 provide a much greater inhibition as shown together with Roche here. Same study was also done with PD-1 VISTA, and that model was recently used by our colleague from BMS, and that helps them to identify VISTA as a ligand for PSGL1, and that ligand work in acidic pH selective condition. So basically, in the tumor microenvironment, the pH will be acidic, and as such, VISTA will bind to PSGL1, and this has been clearly shown, and the combination of PD-1 VISTA clearly provides a much greater tumor inhibition here than PD-1 alone, here in blue. So as you understand, we don't believe that one model is superior to another. It's really a matter of what would you like to study and which are your scientific hypotheses. You may decide to use the BRGSF model as a recipient model for PDX and CDX. You may decide to reconstitute that model with human CD34 positive cells, and you will then have a human immune system. Or you may decide to use the immune checkpoint humanized model that we have, or the T-cell engager model. And all of these models today could be provided to you by ALMOG Diagnostics. So I'm going to stop here, and if you have any question, I'll be more than happy to address your question.
Okay. So there are a few questions in the Q&A part. First one was, what is the conditioning you perform in newborns? It's on the first part of the presentation.
Mm-hmm. So what do you mean by conditioning, please? Could that person here just
you can, yes, you can press allow to talk on the, you can see the questions in the Q&A part. Oh, I see he's answering irradiation.
Oh, irradiation. Okay.
Yeah.
Yeah. So basically, this is irradiation protocol we're using when we use those mice. Okay. So, oops, sorry. So when we go for the newborn animal, the irradiation that we're using here is this is what you these are the doses that we're using here when compared to the NSG here. Okay.
Okay.
So
Another. Yes.
You can use two different methodology. You can use irradiation with newborn, or you could decide to go with a young animal and then you use busulfan, and both work well. We compared both methodology, and we don't see any major difference in the immune system which is developed. When I'm saying any major, I should say we don't see any difference. So you may decide to go with this methodology that we use, which is irradiation. Okay, so the one I just described here, this one, where we do irradiate the newborn. Or you may decide to go with what Roche has did when they use this model. You indeed take young animal and you reconstitute those with, you inject those with busulfan at 15 milligram per kg, and you do your reconstitution. The only difference is that when you do this here, you need to wait another 12 weeks. So the mice that you're going to work with will be older. They will be around 18 weeks old. Okay. Whereas if you do the irradiation protocol, they will be 12 weeks old when you're going to start working with them. But both give rise to the same QC. Just as a reminder, this is what Roche has seen in terms of percentage of human cells. And so with busulfan, and when we do our QC, so I'm just going to take two numbers, 60% of B cell and approximately 14% of T cells. And when we do the QC on the irradiated mice, okay, you're getting 74% of B cell here in our hands. And when we look at the T cell, we're getting 10% of T cell. So we don't see any major difference in those models. I think the second question was
yes.
Percentage of neutrophils. So the percentage of neutrophils is has been studied here. I'm just trying to. Yeah. Percentage of neutrophil has been studied here in this study. And again, upon a BRGSF treatment, we are getting approximately 2%, 3% of neutrophils, okay, versus almost nothing prior to treatment. Okay, in bone marrow and in blood, we're about 1.8%, 1.2%. What was the next question?
Yes,
Sorry.
just I think there is another question from related to this below. Can they be transplanted with no irradiation and no busulfan?
But you mean with human immune cells or with tumor cells? So if the question is, can they be translated with human
with CD34 as newborns?
Yeah, in fact, if you don't irradiate the mice, the human stem cell will still proliferate if you don't treat them with busulfan. So your take rate will be lower because you need to free up a niche for the human cells to develop. We have a new version of this model which has a mutation into c-KIT, a mutation called W41. And that mutation avoids the irradiation and avoids the busulfan treatment. Okay, but that model will be available soon. But if you don't have a c-KIT mutation, if you don't irradiate the mice, if you don't treat them with busulfan, then your mouse stem cell compartment will still be present and will still proliferate. And it's going to be in competition with the human stem cells that you injected.
Okay, we have a question here from Emmanuel.
Okay.
You see it?
Is this one? I'm a pathologist working.
Yes.
Okay. With IC2 to demonstrate immune cells in the neoplasma trio of immunotherapy study. Do you have data of the type antibody? Do you have data on the type of antibody
Antibodies?
anti-human that can be used to show different cell type in the tumor? Do you have data on the type of anti-human? Do you have data on the type of antibody show different cell type in tumor in ICH? Yeah, I see what you mean. In fact, the only study, you have to keep in mind that we provide models to people, okay, and then they do the study by themselves. The only studies that we have in which human cell infiltration was studied in the TME is this study here, and that was not performed by IHC, that was performed by flow cytometry. We are about to run a new study with Champion Oncology in humans, where they are planning to do IHC into the TME, but we don't have those data with us, unfortunately. I'm sorry, Manuel.
Okay, so if there are no further questions, thank you, Kadel, for this interesting lecture. And thank you everyone that you've joined us, and have a great rest of the day.
Thank you. Thank you very much, everyone, for your time, and thank you for this. Oh, sorry, I should have pressed allow to talk. Sorry, I just saw your notes.
Yeah, it's okay. It's okay.
I'm very sorry about that. Sorry. Okay. Yeah, sorry about that. Yeah, so thank you everyone for your time. And I know that was a lot of information, but I really wanted to give you another picture. If you have any questions, you can still contact Nitsan and Yakir and Zid from Almog Diagnostics, and they will transfer those to us, and we'll do our best to answer you back within 48 hours at the latest.
Okay, bye-bye. Good day.
Thank you.